Good morning, everyone.
Good morning.
Today we'll be talking to you about video cards. Brief, give you like what the main core components of them are, as well as what the various names that they are often referred to, and also give a brief history of the video card back to the first computer until now. The video card is also called a graphics card or a graphics or display adapter, or in some cases a graphics add-in board with the graphics word sometimes omitted. It is it's an expansion card which generates a feed of output images to a display such as a monitor. A video card's job is complex, but its principles and components are also complex. Think of a computer as a company with its own art department. When people in the company want a piece of artwork, they send a request to the art department. The art department decides how to create the image and then puts it on paper. A video card, or in some cases a graphics card, works along the same principles. The CPU, working in conjunction with software applications, sends information about the image to the video card. The video card then decides how to use the pixels on the screen to create the image and then sends that information to the monitor. The video card uses four main components in order to complete this task: a motherboard for data and power, a processor or a GPU with which to decide what to do with each pixel on the screen, and memory to hold the information about each pixel and to temporarily store completed pictures, and then a monitor so we can see the final result. The term GPU was popularized by NVIDIA in 1999, who marketed the GeForce 256 as the world's first GPU, or graphics processing unit. A single-chip processor with integrated transform, lighting, triangle setup, clipping, and rendering engines that are capable of processing a minimum of 10 million polygons per second. Rival ATI Technologies coined the term Visual Processing Unit, or VPU, with the release of the Radeon 9700 in 2002. I have a brief video for you all this morning on this subject.
A graphic card is a component which handles the signals that are sent to the monitor or graphics. It is responsible for generating all the text and pictures on your screen. It's called a graphics card because it can be inserted in a PCI slot on the motherboard. 2D or two-dimensional graphics are the kind of graphics displayed when you use a web browser, check email, or work on a spreadsheet. For 2D graphics, the major factors are resolution and refresh rate. Resolution determines how many little dots are used to draw the image on the screen, which are also called as pixels. For example, 640 into 480 means that the whole screen is drawn using 307,200 little dots in 640 columns and 480 rows. The more dots that are used, the finer the detail. And refresh rate refers to how many times a second the image on the screen is redrawn. 60 Hz means that the image on the screen is drawn 60 times every second. This becomes important in a fast-moving video game where the action needs to look real. 3D or three-dimensional graphics are used mostly by first-person shooter type of games. Of course, current monitor technology still only really displays a 2D image, but the player is immersed in a landscape where they can move their character's head and see objects in all directions and move around within this world. This type of display capabilities requires some pretty intense mathematical calculations to be done very fast. The value of a good 3D graphics card is that it offloads most of this work from computer's speed processor, and a specialized processor on the graphic card handles these calculations. This allows for faster, slicker looking graphics. Also, newer 3D cards handles all kinds of additional functions that give surface texture, makes water transparent, etc. So basically, a graphic card will handle all the display work and keep the processor free to perform unlike big jobs.
A GPU is a graphics processing unit and is a specialized electronic circuit designed to rapidly manipulate and alter memory to accelerate the creation of images in a frame buffer intended for output to a display. GPUs are used in embedded systems, mobile phones, personal computers, workstations, and game consoles. Modern GPUs are very efficient at manipulating computer graphics, and their highly parallel structure makes them more effective than general-purpose CPUs for algorithms where processing of large blocks of data is done in parallel. In a personal computer, GPU can be present on a video card, or it can be on a motherboard, or in certain CPUs on the CPU die. The primary suppliers of the GPUs or video chips or chipsets using video cards are AMD and NVIDIA are the two main ones. ATI was bought out by AMD in 2006. In the third quarter of 2013, AMD had a 35.5% market share, while NVIDIA had a 64.5% share. I have a video for you all to watch.
Hey guys, what's up? It's the ESG Tech Buzz here today, and I'm here with another computer basics episode. So today I'm going to be talking about what a GPU is. GPU is kind of like CPU, stands for Central Processing Unit. Both of those two terms have two words in common. That kind of explains for itself. I mean, a GPU processes graphics, and a CPU is, the Central Processing Unit. It's a special card, and not all computers actually have a GPU. You could just have integrated graphics on your motherboard and CPU. This card is designed to process graphics alone, so that's its sole purpose, processing graphics. Now, when I say processing graphics, I mean video editing, animations, but it can also mean your displays. Your GPU can also power your display. And that's the case with most computers, but if you also have integrated graphics, which I know this from experience, the integrated graphics will take over the display when it can to save power. So if let's say you're doing a lot in the background, like you've got Final Cut Pro open and you're rendering out something or Adobe, then that GPU is going to take over the display and the programs. There's a little background information on that. GPU has special RAM on the inside. It's called VRAM, and this RAM is very fast and it's meant to handle graphics. It also has special outputs on the side of it for VGA, well not VGA so much anymore, VGA is pretty old. DVI, which stands for DisplayPort. It also has HDMI on it. So you can plug in your display through the GPU on the back of your computer. Now, these graphics cards have CUDA cores in them. So what the heck does that mean? Well, it's kind of like mini processors, and most GPUs have over 1,000, the newer ones all do, and that stands for Compute Unified Device Architecture. So CUDA cores are programmable cores, basically, on the GPU. For gaming, for instance, which also GPUs handle in most cases, pretty much every case if you've got one. You can set it so the GPU uses some CUDA cores, X amount of percentage for textures in the game, another for lighting, and so on. You can program the CUDA cores to do what you want them to do. So that's really cool. And programmers do that. Certain motherboards and GPUs work together.
I also have an example of a video card with me today. It's actually dead because it overheated. And it was a PNY NVIDIA GeForce 7600 GS. On the history, IBM first created the video card in 1961 as a replacement to printed cards, which were used by the large computers of the day. IBM featured the first video card included on a mass-produced computer in the Model 8088, which was the first personal computer. MDA's monochrome display adapters, the original name of video cards at the time, were only able to work when the computer was in text mode. These cards had 4 megabytes of memory and fit 80 columns and 25 lines per screen. The only color available for a screen at the time was green. Later in the 80s, red was also the screen color, but the card only displayed either red or green. Several types of video cards were introduced during the 80s. The VGA, or Video Graphics Adapter, became the next generation video card. VGAs became more accepted than the earlier MDAs because of their ability to display a range of colors at a better resolution. Because of this, many companies such as Cirrus Logic and ATI entered production at a time when computer components were widely adaptable with each other regardless of manufacturer. Soon after came Super VGA, or SVGA, which boasted a 256 color range and featured up to 2 megabytes of memory. This standard lasted through the middle of the 1990s until the next generation video card arrived. 3D, first created in 1995, 2D and 3D video cards had the ability to show multi-dimensional graphics that were previously unavailable. This was then followed 2 years later by Voodoo, which was the most powerful graphics chip at the time. Together, the video card and chip accelerated the ability of software developers to create more in-depth graphics. Comparable chips such as TNT were created soon after. Intel designed an accelerated graphics port. This helped gap the problems between the video card and the new microprocessors. In 1999, NVIDIA became the dominant manufacturer in the video card market. 3D video memory has now improved from 32 megabytes up to 125 megabytes. An alternative to video hardware can be integrated into the motherboard of the CPU. Motherboard-based implementations are sometimes called onboard video. Almost all desktop computers with integrated graphics allow the disabling of the integrated graphics chip in BIOS, or in some cases the device manager, and have a PCI or PCI Express slot for adding a higher performance video card. The advantages of integrated include cost, compactness, simplicity, and low energy consumption, and the disadvantages because the graphics processor shares system resources with the CPU and RAM and can slow it down. A video card has its own RAM, its own cooling system, and its own GPU. Upgrading to a dedicated video card offloads work from the CPU and system RAM, so not only will graphics processing be faster, but the computer's overall performance may also improve. Does anybody know whether their computer uses integrated or video card? Integrated? Anybody else have anything that they know whether or not they have the video card or integrated? Video card. Does it work out pretty well for you? The advantages, aside from that, the disadvantages on the video card is that sometimes it'll take up, they're big and bulky, and they'll take up either multiple slots or a lot of room. It can be a problem for cooling, as well as possible airflow because they're so big. Power demand. As the processing power of video cards has increased, so has the demand for electrical power. Current high-performance video cards tend to consume a great deal of power. For example, the GeForce GTX Titan is 250 watts. While CPU and power supply makers have recently moved toward higher efficiency, power demands of GPUs have continued to rise, so the video card may be the biggest electricity user in computers, although power supplies are increasing their power too. The bottleneck is due to the PCI Express connection, which is limited to supplying 75 watts. Modern video cards with power consumption over 75 watts usually use a combination of 6-pin 75 watts or 8-pin 150 watt sockets that connect directly to the power supply. While manufacturers of high-end video cards may recommend a minimum power supply of 500 watts in a computer, a power supply of at least 750 watts is typical in a gaming computer with a single high-end video card. Providing adequate cooling becomes a challenge in such computers. Computers with multiple video cards may need power supplies in the 1,000 to 1,500 watt range. Heat extraction becomes a major design consideration for computers with 2 or more high-end video cards. And then prices. An entry-level video card with such as the EVGA GeForce 8400 GS sells for around $30. Many of the best-selling video cards are priced between $100 to $500, and the high-end video card can cost up to $500 or more. And expensive video card marketed to enthusiasts, primarily gamers, the EVGA GeForce GTX 780 Ti is priced around $700. And around $1,000 is the Asus GeForce GTX Titan, which may seem extreme, but a single card can replace multi-card setups, reducing energy consumption and therefore system cooling requirements. Beyond the enthusiast segment is the market for professional video cards, for workstations used in the special effects industry and in fields such as design, analysis, and scientific research. NVIDIA is a major player in the professional segment. In November of 2013, AMD introduced a so-called supercomputing graphics card designed for data visualization in finance, oil exploration, aeronautics, and automotive, design and engineering, geophysics, life sciences, medicine, and defense. Some video cards can be linked together to allow scaling of the graphics processing across multiple cards. This is done either using the PCI bus, express bus on the motherboard, or more commonly, the data bridge. Generally, the cards must be of the same model to be linked, and most low-power cards are not able to be linked this way. Cards from different manufacturers cannot be used together for multi-card scaling. If a video card has different sizes of memory, the lowest value will be used, with the higher values being disregarded. Currently, scaling on consumer-grade cards can be done using up to 4 cards. AMD and NVIDIA both have proprietary methods of scaling. Crossfire X for AMD and SLI for NVIDIA. And I have a video for you all to watch.
And they can support this thing called SLI, or Crossfire X. Crossfire X is AMD's way of saying you can connect 2 of these GPUs at once and get double the performance. SLI is NVIDIA's way. So those are 2 GPU companies, if you didn't know. And it allows you to connect more than 1 GPU to the same system and get double the performance. GPUs can get very expensive. In the previous episodes, I talked about CPUs. I said the CPU is the most expensive component in the computer. Well, it can vary between GPU and CPU, in the computer that is. Monitors.
Does anybody know the difference between the 2 methods? I have a video that will explain both the differences between the methods.
But first, the basics. Both technologies are pretty much a way to utilize more than one graphics card working in tandem in your PC to achieve next-gen class performance that wouldn't otherwise be available with the current technology due to power, thermal, or other limitations. Think of it kind of like if you could buy two Xbox Ones, bolt them together, and actually run your games at 1080p. Ha! Burn! Anyway, they both work with anywhere from 2 to 3 or even 4 compatible cards in one system and perform their best at high resolutions with graphically demanding games. They also both dramatically increase the power consumption and heat output of your computer system without having a proportional impact on the performance you'll get in games. In fact, another thing they share in common is that if the game doesn't have a profile implemented, they will not improve performance at all. But with that said, if you're looking for an experience that simply isn't available today by other means, like buttersmooth 4K or 1080p surround gaming, then you're likely one of the folks that this solution was designed for. All right. So a moment ago, I mentioned compatible cards. This is differentiation point number 1 for AMD. While NVIDIA allows mix and matching of vendors and clock speeds, you can SLI an EVGA reference card with a SUSE overclocked one, they require you to use exactly the same graphics processor with the same memory configuration. AMD, on the other hand, is pretty loosey-goosey. You can mix vendors, clock speeds, RAM amounts, and even the graphics processor, as long as the cards are within the same architectural family. So for example, a 7970 3GB card can crossfire with a 7950 with 3GB, or even an R9 280X with 6GB of RAM, because they're all based on that same GPU. Differentiation point number 2 for AMD is cost. NVIDIA requires SLI certification for your cards to recognize your system as compatible and activate their Wonder Twin powers. For that, NVIDIA requires the qualifying PCI Express slots to run at 8x minimum, even though these days a 4x PCIe Gen 3 slot is plenty for pretty much any graphics card, and they require the board manufacturer to pay a licensing fee. You can find AMD Crossfire compatibility on product pages for like business class boards. Basically, anything goes as long as it's got a couple of PCI Express 16x physical slots. Differentiation point number 3 is something that's actually still a work in progress for AMD. Since the beginning of dual GPU solutions with Voodoo SLI, there's been some kind of connector attaching the cards. With AMD R9 290 series cards, and presumably future ones as well, all communication between the cards is done over the PCI Express bus. It's a higher bandwidth, cleaner looking solution to the problem of how these cards can sync data with each other at high speed when they're working together. Finally, differentiation point number 4 is that AMD allows their cards, their low-end cards, to run in crossfire with the onboard graphics of their APUs, which are CPUs that have strong onboard graphics components. Although the solution still needs some work to be something that I really recommend. And I guess that's it. I guess that's the philosophical difference between AMD and NVIDIA. NVIDIA locks things down, which gives them tighter control over the consistency of the user's experience, but AMD offers more flexibility and choice. Even if some of these options aren't the best thing ever, at least you can pick them.
Are there any questions? That's all I have for you today. Thank you.